Another reaction that we can produce with amines is the Hofmann elimination. And we can relate this to the elimination of alcohols that we learned about in first semester. We all remember that you can take the alcohol, protonate it, make it into a good leaving group, it gets eliminated, and you end up with an alkene. Well, you can actually do the same thing with an amine if you manipulate it a little bit. As it stands here, we've got a really poor leaving group. Even if we protonate it, it's still not very likely to leave. However, scientists found that if we add a number of methyl groups, so basically we're going to exhaustively methylate this amine. So we're going to add as much methyl iodide as the molecule wants. We're going to form the ammonium cation with an iodide counterion. And if we mix that with silver oxide, heat, and water, the silver oxide reacts with the water and the iodide anion to make hydroxide. And basically we eliminate one of the beta hydrogens to produce the alkene, trimethylamine. And we do produce water too, but since we started with that, that's not very exciting. But really the end result is that we've eliminated the nitrogen group from our original organic molecule, and we're left with an alkene. It's the least substituted alkene that is formed because of sterics. So let's look at that a little more closely and see if we can rationalize why the least substituted alkene is formed. So here's another example that will show you how the least substituted alkene is formed here. So that's the ammonium with the iodide, silver oxide, water, and heat. So you can see that we form one hexene, not two hexene. So it's the least substituted alkene that is formed. So let's take a closer look at that on the next slide. I'm going to redraw my ammonium cation. Now, this ammonium cation is rather bulky. It's much like a T-butyl group in that position, so it does have a large amount of steric bulk associated with it. If you remember, we want to, when we remove the beta hydrogen, we need a 180-degree dihedral angle between the beta hydrogen and the leaving group. And it's easiest to see that if we draw a Newman projection. So I'm going to draw two Newman projections here. I'm going to draw the first one showing, looking along the CC bond in the middle of the molecule, what we might experience if we're going to try to form the more substituted alkene. And so my Newman projection here, if I'm looking along that arrow, I would have the 3-carbon chain right there. That's a CH2, so I'd have 2 hydrogens. And then I would have the ammonium group, and I can go on either of these in order to be 180 degrees from the hydrogen. So I'm just going to put it here. I could put it on the left side without any change in this discussion. And then attached also to that is a hydrogen and a methyl group. And that is a stereocenter. We didn't specify any stereochemistry, so I'm just going to leave it like this. And so you see that 180 degrees from the leaving group is that hydrogen that I underlined in blue. And if I wanted to use this other hydrogen circled in black, I could certainly do that. I just have to rotate the back carbon. But the issue here is the 3-carbon chain on the front carbon and the large T-butyl group are gauche to each other. There's no way to avoid that in order to get 180 degrees from the leaving group. So we have this steric hindrance in this orientation because of the large bulky ammonium cation. Let's look at using the other beta hydrogen, and I'll use that, denote that with a green arrow, and I'll draw my Newman projection in green so we can look at that. So the front carbon here will have 3 hydrogens attached to it. It's just a methyl group. And then as I've drawn on the page, the blue molecule has my ammonium right here. And then I have a hydrogen, and then I have a 4-carbon chain attached to that back. So I have 1, 2, 3, 4. And let's see, so now again, this hydrogen is 180 degrees from the ammonium. Any of those hydrogens on the front could be, it's a methyl group. But you can see how the large chain and the large bulky ammonium group, much like a T-butyl, are not gauche to each other. So there's no steric hindrance here, or less, I should say. And so this H is favored. This H is favored. And thus we get the less substituted alkene product.